Hi guys, it's Mrs. Harmison with your Chapter 12 Advanced Chemistry Notes. This chapter is about chemical kinetics, which is the area of chemistry that deals with the rate at which reactions take place. Previously, we have discussed factors that made reactions happen faster, like increasing temperature, concentration, and surface area. In this video, we will learn to do some more complex calculations with chemical kinetics. The reactants, as a reminder, are on the left side of the arrow in a chemical equation, and the products are on the right. Anytime that you see brackets around a substance, that means that we are talking about the concentration of that substance. Usually these concentrations are going to be in units of molarity. First calculation involves decomposition reactions. This is when you have one reactant that breaks down into two or more products. This is the equation that we're going to use for average rate of disappearance of a reactant. The delta here means change in, which means you're going to take the concentration of the reactant you're dealing with at the end minus the concentration reactant that you're dealing with at the beginning, divided by, and we'll make that negative, the T2 minus the T1. The units for our molarity and the units for time can be seconds or minutes or hours, depending on the data you're given. So for this specific problem, it's asking us to find the average rate of disappearance of the hydrogen peroxide over the time period from 19 seconds to 38 seconds. So we're going to call 38 seconds our T2 and 19 seconds our T1, which makes this the concentration 2 and this the concentration 1. So we will plug things into this equation. Also, I wanted to point out this second to the negative 1 is the same as per second. You're going to see that a lot in this lesson. We use stoichiometry along with chemical kinetics. For this time period, it is telling us that there's 3.29 times 10 to the negative 6 molar per second of an increase for every 1 mole of NaCl. Our balanced equation tells us that there are 2 moles of NaCl for every 1 mole of chlorine. To calculate a reaction order, you would need to be looking at a set of reaction data, but we're just going to talk about what the different kinds of orders mean. If a reactant is a zero-order reactant, the rate does not change when the concentration changes. For a first-order reactant, the rate increases by the same factor as the concentration increases. So if you took the concentration of reactant A times 2, then the rate would be also twice as fast. For a second order reactant, the rate increases by the factor that the concentration increases by squared. So if you took the concentration of reactant A times 2, the rate would increase by a factor of 4 because 2 squared is 4. And then in order to calculate the total reaction order, you just add up all of the orders of the reactants. It is the sum of the reactant orders. This is the rate law formula. The rate is going to be measured in molarity per second. K is the rate law constant. It's going to have a variety of different units depending on how many reactants we have and what the orders of them are. A in brackets stands for the concentration of reactant A. B in brackets stands for the concentration of reactant B. M stands for the order of reactant A, and then N stands for the order of reactant B. Sometimes you will see these abbreviated as X and Y, but on your OWL program, they're M and N. All right, this question is asking us to complete the rate law reaction for this specific chemical reaction. So we're going to start with the rate, and you're just going to put a K in for the rate constant. You don't actually need a number. Our first reactant is NO, so we put NO in the brackets. Make sure you make them both capital. It tells us here that it's second order in NO, so we're going to put squared because M is second order, so we put a 2. It tells us also that it's third overall. So if we know that the entire reaction order is 3 and NO is 2, then we know that this must be a 1, so it must be first order in O2. So then we're going to put brackets around O2, the second reactant, and when it's first order, you just assume the 1. You don't actually write it. So this right here is exactly what you would type into that box. Okay, this time they're also asking us to write the rate law for this specific reaction. So we're going to start with K, and then we're going to put the first reactant in brackets. Now, when you put something in like this, make sure that the I is capital and the L is lowercase and the K is lowercase. And then it tells us that it's first order in ICL, so we don't write anything here. Our second reactant is H2, and it's second order in H2, so we put squared there. So this is our rate law, but then it also gives us the data and asks us to calculate the rate of the reaction. So we're going to calculate rate. It tells us 2.06 is the rate constant, and the concentration of ICL is 0.215, and the concentration of H2 is 0.127. So we need to square that because we have a squared in our rate law, and we calculate, and I got 7.14 times 10 to the negative third, and that would be molar per second. That's the same as this unit with that -1. Now you need to be able to do these where you're calculating for rate, but also if they gave you the rate, you would need to be able to calculate for the rate constant. These are the formulas you will use for calculating kinetics of a decomposition reaction. They're slightly different for each order, but in all of the orders, these variables remain the same. Brackets around the reactant mean the concentration of reactant A. The same thing here, but with the 0 down here means the initial concentration of reactant A. K stands for the rate constant, T stands for time, and then T1/2 stands for half-life. Concentration is going to be measured in molarity. And again, the rate constant will have different units depending on which order we're dealing with. The time can be measured in seconds, hours, minutes, days, etc. And then the half-life is going to be measured in inverse units of time, like seconds to the -1, or hours to the -1, or minutes to the -1. And that has to match up with the unit of time for the variable T. It tells us that in this reaction, the decomposition of H2O2 is first order. So I put our first order equation here. It has a rate constant of 1.1 times 10 to the -3 per minute. It has an initial concentration of H2O2 of 2.02 times 10 to the -2 molar. And it's wanting us to calculate the concentration of hydrogen peroxide after the reaction takes place. And we have the time we're going to allow it to react is 1,495 minutes. So we have the same units here, minutes and per minutes, so that's good. We can just plug it into the equation. The natural log of the initial concentration divided by what we're trying to solve for, so we can put that in as an x, equals K, which is 1.1 times 10 to the -3 times our T, which is 1,495 minutes, and then we can solve for x. Okay, when we multiply these two numbers, we get 1.6445. And then to get rid of this ln, we have to do the inverse, which is e to the x. So you do second ln, which means you are taking e to the 1.6445. So again, you're typing second and then the ln button to get rid of this natural log. And then you just solve for x. And for this one, I got an answer of 0.0039 molar. Now you're going to need to be able to use this equation to solve for either the concentration or the time or the rate constant. All right, in this one it tells us that it is second order. So I put our second order equation here for the decomposition. So we want to solve for the concentration after. So we're solving for this A right here. And it tells us a time, and it tells us the initial concentration, and it tells us the rate constant. So we're going to plug 1 over this is the concentration we're trying to solve for, is equal to 1 over the initial concentration, which is 1.94, plus the rate constant, which is 1.1 times 10 to the -3 times the time. And we look and make sure that the seconds and the per seconds are the same units, and the time is 1.35 times 10 to the 3rd, and we solve for x. Is a zero order example. It tells us it has a rate constant of that, and that's going to be our K. The initial concentration is this, so that's going to be A naught. It tells us the current concentration of A, and it wants us to solve for time.